Okay, this is the second part of the video. Just left you doing those calculations there, and now going into examples of conservation of momentum. And there's one here, and I've got one in the lab. Again, thing I'd love to show you sometime. Some people have seen it before who I've taught in GCSE, and it's Newton's cradle. This is where you find the very, very wealthy chairman or executive of the company. When they get stressed out, they have one of these in their desk. What you've got is long threads like this, and you've got metal spheres hanging down. Now, first of all, what is you've got all the balls attached together like this, and what you do is you bring one ball back here, and what you do then is this. Let go, it hits the balls here, and then one leaves. Now, why this is happening, and I'm going to try and freeze it as it goes down, bang. When this one hits here, it transfers, well, it's a force on next ball, therefore it transfers momentum. But because they're all in contact, it keeps transferring momentum to each ball. But when it gets this ball here, it's got nothing to transfer momentum to, therefore off it goes. But if you treat nice simple numbers, pop them way around a little bit, if this moving down with a velocity 1 and mass 1, therefore its initial momentum is going to be 1. And therefore at the end, oh dear, it's all going to be haywire now, isn't it? When that ball leaves and this one goes off over here, this also is going to have momentum 1, therefore it leaves a velocity 1 because it's got mass 1. Now, the cool things you can do with this is you can take two balls, this and let go, and what's going to happen? 2 hit and 2 leave, which makes common sense, doesn't it? Because now, if I freeze it, if this has got now mass of 1, the total mass is 2, moves down velocity 1, initial momentum is going to be 2. And then leaving here, you've got 2 balls leaving, and each ball must leave, 2 balls must leave velocity 1, therefore momentum at the end must be 2. If I then take 3 balls and play, 3 leave. And if I now reset, it starts getting really weird, because then, oh dear, don't do that, you. If I then take away 4 balls and let go, really weird. But it still has conservation momentum. 4 hit, 4 leave, 4 hit, 4 leave. And if I reset it, one of the most weirdest one of all is now where you've got 1, 2, 3, 4, 5 balls, and it goes down, and therefore you've got 5 hitting, 5 leaving. And again, conservation momentum is being held true. Really nice little simulation of that. Look it up yourself if you want to. The website link is up there so you can see it. Now, to go with that then, is you need to know about elastic collisions. Now, elastic collisions, what I do is think about balls being very elastically. Therefore, like a ball, bang, hits a bouncy ball, hits the ground, bounces up again. Now, elastic collisions, what that is basically, the whole crux behind it, is when you're going to have kinetic energy must be conserved. Okay? Therefore, the total kinetic energy before and the total kinetic energy afterwards have to be the same. And you'll find that in your book, and it's under, it's the 1.4 in the old book, and you'll find it in the new book on that PDF copy. I'm not sure what chapter it's on at the moment, to be honest, but it's that one holds true. Now, to show you elastic collisions is, I'm going to go into this lovely bit of software just here. So this is, I'll use this quite a bit actually because it's a really good piece of software. Here we go. Now, making this bigger so you can see it. Here you've got truck A and truck B. Now, truck B is going to be stationary and truck A is going to hit it. And I'm going to make this a total elastic collision. Therefore, this has got mass of 1, that's got mass of 1. This has got velocity of 2, that's initially going to be 0. So when they go along and hit, because they are going to be elastic, okay, that one is going to transfer all the energy to this one, and off it goes, it moves off. Now, do we have conservation momentum? Well, the momentum before of A was going to be 2, because its mass is 1 and the velocity is going to be 2. And therefore, the initial momentum of B is 0 because its velocity was 0. At the end, because this one is stopped, the total momentum of A at the end is going to be 0. And at B, the momentum of this one must be 2. can you see if you have the initial momentum is going to have 2 and a final momentum is also going to be 2? Yes, it is held true. When I go to kinetic energy, I'm using equation half mv squared, but then you've got ua squared because that's the initial velocity. You plug your numbers in, half times the mass times velocity squared, and you get 2. B, because it's stationary, is going to be 0. Therefore, when they go wallop and hit together against each other here, at the end, A has got no velocity, therefore it goes down then to 0. And B is going to have final kinetic energy is going to be 2, because it's going to be half mb multiplied by the final velocity squared. Can you see the total kinetic energy before is equals to total kinetic afterwards? Kinetic energy has to be conserved. And then give you another example here, which I now can make this one going to be 3 kilograms. Again, I can fire it going through, check the numbers, and you do this yourself. Okay, this is where now it rebounds, which is quite interesting. If you look again here, total momentum 4 is going to be 2. But now afterwards, it's got -1 and 3 because that's bounced away negative because it has -1 of the velocity. Kinetic energy before, I've got 2 and a 0. Afterwards, I've got 0.5 and 1. Remember, kinetic energy is a scalar quantity. It's not more about direction. Therefore, see, total kinetic energy, again, is going to be 2. So that has explained what is meant by elastic collisions. And my last part of the video is now I'm going to start moving on to inelastic collisions.